Welcome to the lecture series on numerical methods. In the last lectures we have discussed about numerical differentiation, and today we will start about numerical integration. So, in the numerical integration we will just deal different kinds of interpolation formulas and how we can just integrate this polynomial or this function with using this interpolation formulas. So, specifically the advantage of this numerical integration is that if we will have this specific nodal points with its tabular values, then at that point if the function is not known to us explicitly, we can use these numerical integrations to evaluate these functional values at all of these points or wherever these points are asked to evaluate. So, first we will just go for this introduction, that where we are just observing these difficulties of the solving problems in integration and why we are just going for this numerical integration. Then we will just go for this methodology for numerical integrations, and obviously for this lecture we will just go up to the rectangular rule, that how we can just use this rectangular rule to evaluate this integration. So, specifically if you will just go for the history of integration, you can just find that Archimedes has developed this integration to find the surface areas and volumes of solids, and this integration method was very modern nowadays, and since earlier it was just developed to calculate this area or volume or solids, volume of solids in sphere or in cones. Gauss was first introduced to make the integrals in a graphical sense. This means that graph for integrals he has developed, and Leibniz and Newton discovered the calculus and found this differentiation and integration which are converts to each other. So, integration was used to design, or it can be applicable to many fields of science and engineering if you will just see. And here I am just showing some of this modern infrastructures where this integration was used, like Petronas Tower and Sydney Opera House, or finding the curves under the center of mass, displacement, velocity and fluid flows. Specifically without integration and derivative we cannot solve such type of problems. So, if you will just go for this integration, if somebody is asked what is integration, so then especially we are just putting a curved sign, and which is just giving a parametric region where we want to evaluate this integration or calculate these areas or surfaces or volume bounded within that surface. And if we are just defining these integrals, so integrals are of two types. First it is called definite integral, where this end points should be finite and we can just easily position these points. And the next is that indefinite integral. If some ranges are infinite, then especially it is called a indefinite integral, where it is difficult to evaluate the functional values within that range. So, in such of cases, so if you will just go for like definite integral or finite range integrals, so especially we are just defining a range there. Y has a range like y equals to like 0 to some range suppose, and x has a range like x equals to 0 to suppose a, or x equals to a to b, and within that point how this y curve is approximating or how this variation of y is occurring, that we try to estimate with the axis bounding region with this curve there. This means that if y equals to f of x is a function is defined, and how this area is occurring or how this areal interaction or this enclosure is occurring within this x axis for two fixed points, that can be evaluated by using integrations. So, why we are just going for this numerical integration? If the function f of x is not given, as I have told you, but the values are given at distinct points, then we can just use numerical integration to find these values of the function within a given range. Sometimes if some of these complicated functions, if it is given like e to the power minus x square suppose, within the range of like 0 to 1 dx, so it is very difficult to carry out, and in that case if you just go for numerical integrations, it is very easy to evaluate the integrations. Let us suppose that the functional values are known at x equals to a and x equals to b, and suppose a and b is divided into n equals. This means that n minus 1 internal points in AB. Suppose these internal points we are just naming as x1, x2 up to xn minus 1. So, if you will just visualize this one in a graphical sense here, suppose we will have these points like x equals to x0 to x equals to xn suppose. Then we can just divide this range x equals to x0 to x equals to x1 into suppose n sub intervals. So, we will have now this n minus 1 internal points like x1 to x2, x3 up to xn minus 1. Obviously, we can just write, or sometimes for convenience we are just expressing x naught equals to a and xn equals to b. Then we can just define these points are as a equals to x0 less than x1 less than x2 less than up to less than xn minus 1 less than xn, this equals to b. So, if we are just approximating any function with a polynomial approximation within this range, suppose x0 to xn here, then we can just obtain a polynomial within that range. So, in that range we will have n plus 1 nodal points with n sub intervals like xi plus 1 if I is varying from 1 to n minus 1 here. So, if we will just approximate this function with a polynomial, or we want to fit the polynomial p of x over suppose k sub intervals here, passing through the points like xi, yi here, I equals to 0, 1, 2 up to k, and evaluate this integral. So, then we can just write I1 as x0 to xk f of x dx, or we can just write this one as x0 to xk p of x dx here. Obviously, if it covers, or obviously it covers k intervals like xi to xi plus 1 for I equals to 0, 1, 2 k here, and this process is repeated for all the intervals. This means that first if it covers k intervals, then in the repeated process in the next interval also it can covers like k intervals again until over the entire domain should be covered off. Then we will just go for the discussion of this numerical integration in a different interpolation formulas. First we will just go for this Lagrangian formula here. So, if you will just write this Lagrangian formula for this polynomial approximation is usually written in the form of summation of like I equals to 0 to n Lix f of xi, where Lix is called Lagrangian polynomial coefficients, and usually this Lix is expressed in the form like omega of x divided by x minus xi into omega dash of xi there. Specifically, if we will just write in elaborated form, then we can just write Lix as x minus x0, x minus x1 to x minus xi minus 1, x minus xi plus 1 up to x minus xn divided by xi minus x0, xi minus x1 up to xi minus xi minus 1, xi minus xi plus 1 up to xi minus xn here. If you will just write this integration here, this integration can be written as integration of x0 to x1 f of x dx. Suppose this can be written as, or if we want to write this one as x0 to xk, suppose in each of these intervals if you will just evaluate x0 to xk f of x into dx, this can be written as x0 to xk summation of I equals to 0 to n Lix f of xi into dx here, or it can be written in the form of summation of I equals to 0 to n f of xi integration of x0 to xk Lix dx here. Already it is known that Lix can be expressed as the coefficients of x here, which can be written in the form of either in the form of omega x by x minus xi into omega dash of xi there. So, if we will just implement the numerical integration for all these product terms there, then we can just evaluate this numerical integration for this polynomial there. So, next we will just go for this numerical integration using Newton's forward difference formula. When the values of the function y equals to f of x are provided, suppose at equally spaced abscissas, then we can just use this Newton's forward difference formula. And in finite difference approximations, usually this Newton's forward difference formula in polynomial form are written as y0 plus p delta of y0 p into p minus 1 by factorial 2 del square of y0 plus p into p minus 1 p minus 2 divided by 3 factorial delta q of y0 plus of to finite number of terms, that is as p into p minus 1 p minus 2 of to p minus n minus 1 divided by n factorial nabla to the delta to the power n of y0 here plus the remainder term. So, if you just replace in terms of x here, usually we are just replacing here x equals to x0 plus ph here. So, that is why p can be written as x minus x0 by h here, and if you just replace this p values in terms of x here, then p of x can be written as y0 plus x minus x0 by h into delta of y0, then x minus x0 into x minus x1 by 2 factorial h square del square of y0 plus all other terms in the same fashion. So, if we will just write this polynomial in terms of p, usually we can just denote that one in terms of a p here, that is p of p can be written as y0 plus p delta of y0 p into p minus 1 by 2 factorial del square of y0 up to p into p minus 1 up to p minus k plus 1 by k factorial del to the power k of y0 there. So, if we will just use this integration for this formula here, then we can just write integration of x0 to xk p of x dx here, or it can be written as x0 to xk f of x dx. This equals to, we can just write h into integration of like 0 to, since x0 to xk here, 0 to k we can just write, and p of p into dp here. Since if you will just see here, dx is nothing but h dp, if you will just write this one. So, that is why this h is coming out, and at this point x equals to x0, if you will just put p equals to 0, and if you will just put x equals to like xk, that is nothing but x0 plus kh. So, that is why p equals to k there. So, that is why we are just changing this interval, that is in this form here. So, in this regard also we can just write this error terms also. So, usually this error terms are usually written in the form like x minus x0. So, for this Newton's divided difference formula, if you will just write this error term, that can be written as, so this error term for this Newton's interpolation formula r of x can be written as p into p minus 1 into p minus 2 up to p minus k k, if you will just write up to kth term here. So, we can just write in this form, or divided by, you can just write k factorial here, and del to the power, sorry, this is k plus 1 factorial here, and del to the power k plus 1 y0 here. And in terms of x, if you will just write, this can be written in the form of like x minus x0, x minus x1 up to x minus xk divided by k plus 1 factorial, and it can be written also h term, it is also there. So, that is why we can just write this one as f to the power k plus 1 zeta divided by k plus 1 factorial here. So, if you will just integrate this one within this range of x0 to xk here, so this can be written as x0 to xk r of x dx. This can be written as x0 to xk here, like x minus x0 to x minus xk here divided by k plus 1 factorial f to the power k plus 1 zeta here, where zeta should be lies between x0 to xk here. So, if we will just take out this term like f to the power k plus 1 zeta by k plus 1 factorial as that are constant, so it can be taken out. So, inside this integration, so we can just write x0 to xk, x minus x0, x minus x1 to x minus xk into dx here. So, if we will just eliminate dx as in the form of hdp here, so then x minus x0 and x minus x1 in terms of p here. So, we can just write that the total term can be written as h to the power k plus 2. This can be written as h to the power k plus 2 divided by k plus 1 factorial f to the power k plus 1 zeta, integration from 0 to k, p into p minus 1, p minus 2 up to p minus k plus 1 here into dp. Sorry, this should be p minus k up to that one, since x minus fk is there. So, this is the integration formula. So, if you will just go for this like total error in computing the integral I equals to x0 to xk f of x into dx, then sum of the module of errors, that is the number of times it is just occurring in each of the intervals, that can be taken off, and sum of all these terms to cover off these error terms in each of these intervals x0 to xn. So, now we shall discuss some of the methods that are based on equally spaced abscissas. Suppose that the interval AB is subdivided, suppose n sub intervals here, each of which suppose h here. Then we can just define h equals to b minus a by n here. So, suppose in a graphical sense, if you will just visualize, we can just define x0 to xn up to xn equals to b here. So, then we can just define, if all these points are equally spaced here, then we can just define h equals to b minus a by n, or we can just write xn minus x0 by n here. And each of these points, since it is equispaced here, we can just write xi equals to xi minus 1 plus h here, where I is varying from like 1 to n here, incremented by 1. So, and we can just define these points, that is in the form of like a equals to x0 less than x1 up to less than xn equals to b here. And if you will just go for this rectangular rule, suppose in the rectangular rule form, usually this method is applicable whenever we have a constant value of function which attains its maximum value within that range. This means that if suppose we will have a integration range from x0 to x1, then we can just assume that y0 or these functional values at x0 can be considered as a constant value for f of x within the whole interval there. And in the second interval, the same fashion we can just approximate that one y1 as f of x1 throughout the interval. And in that case, we can just write this integration as in the form of like a real cross section, and within that if you will just divide each of these intervals in rectangular sections, like if suppose we will have this integration range y equals to f of x is given to us, and it is asked to evaluate this integration within this range a to b. Suppose we can just subdivide this total regions into n sub intervals here, and if you will just take this small section as a straight line, or these perpendiculars we can just draw at each of these points here, since sufficient closed intervals we are just considering. So, that is why the error of approximation should be minimized in this sense here. If you will just consider the starting point as x0, next point is x1 and next point is x2, likewise the last point is xn here, and corresponding y values are like y0, y1, y2, likewise the last point will be yn here. Then we can just consider this integration within this range like x0 to x1 y of x dx or f of x dx, which can take the maximum value y0 within this range x0 to x1 here. Then we can just write this integration as y0 into x1 minus x0 here, and this can be written as h y0 here. So, similarly we can just define this integration range like a x1 to x2, x2 to x3 in the same fashion, and adding of, if you will just add of all these areas like x0 to xn, suppose y of x dx or f of x dx, this can be written in the form of like x0 to x1, x1 to x2 up to xn minus 1 to xn f of x dx here. Then each of these intervals we can just, first interval we can just obtain h of y0, second one we can just obtain h of y1, and third one we can just obtain that one h of y2. So, likewise if you will just sum of all these terms here, then the final integration we can just get it as h into y0, y1 up to yn minus 1 here. And if the function is suppose monotonically increasing, then we can just write integration a to b f of x dx is greater than h of y0 plus y1 to yn minus 1. If suppose it is monotonically decreasing, then we can just define as integration a to b f of x dx is less than h into y0 plus y1 to yn minus 1 here. So, then we will just go for like a rectangular rule used for Lagrange's formula. So, in the Lagrange's formula, suppose if the interval is given like x0 to x1 and it is asked to fit with a polynomial passing through the points like x0 y0 and x1 y0, suppose, since the functional values are same at both these points. So, then we can just define this polynomial as we will have these points like x0 y0 and x1 y0 here. These functional values remain constant at both these points. Then we can just define this Lagrange polynomial as x minus x1 divided by x0 minus x1 y0 plus x minus x0 divided by x1 minus x0 y0 here. So, then this total polynomial can be written as y0 here. And if you will just approximate this error for this polynomial, then this error terms r of x can be written in the form of like x minus x0 f dash of zeta, where zeta should be lies between x0 to x1 here. And if you will just integrate this linear interpolating polynomial for Lagrange's method, then we can just write this one as x0 to x1 p of x dx. This can be written as y0 into x1 minus x0, that is nothing but h of y0 here. And this formula is the rectangular rule, especially it is called. And if you will just approximate the error terms also, this error term can also be written as e equals to x0 to x1 r of x into dx here, and that can be written as x0 to x0 plus h x minus x0 f dash of zeta into dx here, which can be written as h square by 2 f dash of zeta, where zeta should be lies between x0 to x1. And in the same form, we can just obtain this composite formula for this linear interpolating polynomial in Lagrange's method as a to b f of x dx, that is x0 to xn f of x dx. This equals to h into y0 plus y1 plus y2 up to yn minus 1 here. So, based on Newton's forward formula, if you will just go for this calculation here, like if you will have this function f of x in x0 to x1 by terms of Newton's forward interpolating polynomial here, usually we can just write x0 to x1 f of x dx here, or that can be written in the form of x0 to x1 p of phi into dx here. And obviously this integration range for this p of phi can be transformed to 0 to 1, and dx can be written as h dp here. So that is why we can just write this one as h 0 to 1 into your functional value y0 into dp here, and this especially can be written as h y0. And in the similar fashion also we can just determine the error for this formula, that can be written as e equals to h 0 to 1 p delta of y0 into dp, so which can be written as h square by 2 f dash of zeta. Since we have known that del y0 by h this equals to f dash zeta, so in both these methods we are obtaining the same formula for rectangular rule. Thank you for listening this lecture on numerical integration. Next lecture we can just continue for this numerical integration based on Newton's forward difference formula and all other interpolation formulas.